Hello there, and welcome, dear listener, to the Sleepster, your tranquil sanctuary where the grandest mysteries of the universe unfold with a soft whisper, designed to soothe your mind as it expands with wonder. Here, in this cozy corner of curiosity, we gently explore the intricate tapestry of existence, inviting you to settle in, perhaps nestled under a warm blanket with your device propped just so, allowing your thoughts to drift peacefully towards understanding and perhaps towards a restful sleep. I am truly so glad you've chosen to spend this quiet time with me. Tonight, we embark on a particularly profound journey, one that touches upon the very essence of our experience. We are setting our minds on the quantum fabric of time itself. Imagine, if you will, peeling back the layers of what we perceive as time, that relentless forward march of seconds, minutes, and hours, to peer into its deepest, most fundamental nature. From the fleeting blink of a hummingbird's wing to the vast eon-spanning epochs of cosmic evolution, time seems to dictate every rhythm, every change, every beginning and end we witness. It is the silent, pervasive current upon which all of reality appears to float. Yet, as we shall gently discover, time is far more enigmatic, more fluid, and perhaps even more beautifully strange than our everyday senses suggest. This is the quiet story of how our understanding of time has evolved from a simple, unyielding river to a complex quantum ocean brimming with untold possibilities and unexpected depths. Now, I must confess, I hope this exploration isn't too captivating. For the ultimate goal, after all, is to help you drift off peacefully into the realm of dreams. But if you do find yourself wide-eyed, not from restlessness, but from the sheer, breathtaking wonder of time's true nature, well, at the very least, you'll be wide-eyed and a little wiser, carrying a newfound appreciation for the temporal dimensions that cradle our existence. It's a gentle paradox we embrace here, where profound knowledge meets profound tranquility, before we truly begin our descent into the quantum fabric. I'd love to know if you feel inclined to share where in the world are you listening from tonight, and what time is it where you are in this moment that we share across vast distances. Feel entirely free to leave a quiet comment and just say hello. It's always such a joy to see this calm, sleepy little community stretch across so many time zones and continents, a beautiful reminder that even in our individual moments of rest, we are connected by a shared curiosity. If you find solace and comfort in videos and episodes, life is one equal parts gentle knowledge and serene calma. Quiet tap on the like button or a soft, quiet subscribe helps more than you might know. It's a small, almost imperceptible action on your part, yet it quietly supports hours of careful research, thoughtful writing, and a whole lot of softly whispered wonder, allowing more gentle journeys into science to reach those who seek them. And just before we settle deeply into our topic, a quick, gentle reminder. While this video is woven with interesting scientific concepts and theories, it is purely for entertainment and relaxation. It is not in any way medical advice. If you are finding yourself consistently struggling with sleep or facing any health concerns, it is always best to speak to a qualified professional who can provide personalized care and guidance. This tranquil journey into time is here to relax and stimulate your gentle curiosity, not to replace professional care. All right, let us now settle deeper into our comfortable space. Take a soft, deep breath, letting the day's concerns gently recede, and begin our quiet, thoughtful journey into the most fundamental question of existence, the very nature of time itself, seen through the delicate lens of quantum reality. We'll start by gently touching upon our everyday understanding of time, before we slowly, thoughtfully begin to unravel its more perplexing and beautiful secrets. Prepare to drift. The concept of time is, for most of us, an intuitive given. We experience it as a linear progression, past, present, future. A universal clock ticking steadily, independently of our will or the events it chronicles. This intuitive understanding, often called Newtonian time, paints a picture of time as an absolute, unchangeable, and external dimension. Much like an invisible, rigid railroad track upon which the train of events rolls forward, always at the same speed everywhere in the universe. In this view, if you had a perfect clock, it would keep perfect time, whether it was on Earth, on the Moon, or in the most distant galaxy. Every event, everywhere, could be assigned a precise objective. Time coordinate, and all observers, no matter their location or motion, would agree on that time. It's a comforting, stable framework, one that underpins much of our daily lives. Our calendars, our appointments, our very language. We say before and after, yesterday and tomorrow, confident that these terms hold universal meaning. This classical notion of time feels utterly real, almost tangible in its relentless forward march. We can't stop it, we can't speed it up, we can't reverse it. It simply is. This perspective served us incredibly well for centuries. It allowed us to calculate the orbits of planets with astonishing precision, to predict eclipses, and to build intricate mechanical clocks that marked its passage with increasing accuracy. It fostered the idea that the universe operated like a grand, deterministic machine, set in motion at some initial point and unfolding along a predetermined timeline. For Newton, space and time were the absolute stage upon which the cosmic drama played out, unmoving, unchanging, and entirely separate from the actors and events within them. He famously stated, "Absolute, true, and mathematical time, of itself, and from its own nature, flows equably without relation to anything external." This view provided a robust foundation for classical physics, allowing for the astonishing advancements of the scientific revolution. It felt complete, logical, and universally applicable. And for the vast majority of human experience, from the planting of crops to the construction of cathedrals, this absolute time was all that was needed, a reliable backdrop for the unfolding of human civilization and scientific inquiry. It was the bedrock of our reality, seemingly as solid and unyielding as the ground beneath our feet. However, beneath this seemingly calm and orderly surface of Newtonian time, whispers of complexity and contradiction began to emerge as science probed deeper into the universe. These whispers grew louder, eventually leading to seismic shifts in our understanding, challenging the very bedrock of that intuitive framework. The first major crack in this seemingly unyielding foundation came not from the realm of the incredibly small, which we'll explore later, but from the realm of the incredibly fast and the incredibly massive, the world of Einstein's relativity. Imagine a perfectly still pond, its surface calm and reflective. Newtonian time assumes this pond is infinite and unperturbed, a uniform surface for all happenings. But Einstein suggested that the pond itself could ripple, bend, and even warp, depending on what was moving through it or resting within it. This was a radical departure, a profound reimagining of the stage upon which reality plays out. The special theory of relativity, unveiled in 1905, introduced the mind-bending concept of time dilation. This is where time, rather than being absolute, becomes relative to the observer's motion. It states that time can literally pass at different rates for different observers, depending on their relative speed. Imagine two identical, perfectly accurate clocks. One remains stationary on Earth while the other travels at speeds approaching the speed of light. The moving clock will tick slower than the stationary one. When it returns, it will show less time has passed. This isn't just a theoretical curiosity. It's a phenomenon that has been rigorously tested and confirmed, most famously with atomic clocks flown on airplanes, which return showing a tiny but measurable difference in time compared to ground-based clocks. Even the GPS satellites orbiting Earth experience time dilation due to their speed. And if these effects weren't accounted for, our navigation systems would quickly become inaccurate. Time, then, is not a universal constant, but a personal experience shaped by one's velocity through space. It's as if each of us carries our own subtle, unique temporal rhythm, beating ever so slightly differently depending on how fast we're moving. Then came the general theory of relativity in 1915, which deepened the mystery of time even further by connecting it to gravity. This theory proposed that massive objects like planets and stars actually warp the fabric of space-time itself. Imagine a bowling ball placed on a stretched rubber sheet. It creates a depression. According to Einstein, massive objects do something similar, curving the space-time around them. And just as this curvature affects the paths of objects moving through space, it also affects the flow of time. Specifically, time runs slower in stronger gravitational fields. This means that a clock at the top of a skyscraper will tick infinitesimally faster than a clock at its base, closer to Earth's gravitational pull. Again, this isn't science fiction. It's a measurable effect, crucial for the precise functioning of GPS satellites, which operate in a weaker gravitational field than clocks on Earth's surface, and thus experience time running slightly faster. These relativistic effects, though minuscule in our everyday lives, demonstrate a profound truth. Time is not a separate external entity, but an intrinsic part of the dynamic, interconnected fabric of space-time, bending and stretching with the presence of mass and energy. It is no longer an unyielding river, but a flowing current that responds to the very landscape it traverses. These revelations from relativity were revolutionary, fundamentally altering our perception of time from a universal backdrop to a dynamic participant in the cosmic dance. Yet, even as relativity was painting this astonishing new picture of time as a flexible, malleable dimension interwoven with space, another, equally profound revolution was unfolding in the scientific world: the birth of quantum mechanics. This was a realm not of the very large and very fast, but of the incredibly small. The subatomic world of particles, waves, and probabilities. And as scientists began to peer into this minuscule domain, they discovered that the familiar, predictable rules of our everyday reality, including the smooth, continuous flow of time, began to break down, revealing an even more perplexing and counterintuitive reality. The quantum realm suggested that time, too, might not be as smooth and continuous as we experience it, hinting at a granular, perhaps even fragmented structure at its deepest level. It was here, in the strange and beautiful world of quantum physics, that the true fabric of time would begin to unravel in ways that still challenge our imagination. Consider the quantum world as a realm where precision gives way to probability, where particles can exist in multiple states at once, and where observation itself can influence reality. In this bizarre landscape, the very concept of a continuous, smoothly flowing time becomes problematic. Quantum events often don't have a single, definitive moment of happening. Instead, they operate within a cloud of probabilities, making the classical idea of when an event occurs far less straightforward. Furthermore, some quantum theories suggest that time itself might not be a fundamental property of reality at the deepest level, but rather an emergent phenomenon, something that arises from the collective behavior of countless quantum interactions. Much like temperature emerges from the chaotic motion of individual molecules. If this is true, it would mean that at the most fundamental scale, there might be no time as we understand it. Just a timeless sea of quantum events from which our macroscopic experience of linear time somehow crystallizes. It's a dizzying thought, transforming time from an absolute ruler to a symphony born from countless tiny, probabilistic notes. The very notion of quantum time often grapples with the challenge of unifying general relativity and quantum mechanics into a single, cohesive theory of everything. General relativity describes gravity as the curvature of spacetime, a continuous fabric. Quantum mechanics describes the other fundamental forces, electromagnetism, strong and weak nuclear forces, as discrete packets, or quanta. When physicists try to apply quantum principles to gravity, and thus to spacetime, they encounter immense difficulties. One of the most significant is the problem of time in quantum gravity, which suggests that in some formulations, the variable for time simply disappears from the equations. This isn't to say time doesn't exist, but rather that our current mathematical frameworks may be inadequate to describe it at the quantum level, or that its nature at this scale is profoundly different from our everyday experience. A reality where before and after might not be universally defined, or where the arrow of time itself might only emerge at larger scales. It's like trying to understand the flow of a vast river by examining a single water molecule. The concept of flow only makes sense when you consider the collective. Some theories, like loop quantum gravity, propose that space-time itself is quantized, meaning it's made up of tiny, indivisible units. Much like light is made of photons. If space is granular, could time also be? This would imply that there is a smallest possible unit of time, a chronon, beyond which time cannot be further divided. Much like there's a smallest unit of length, the Planck length. If time is indeed discrete, then its seemingly smooth flow would be an illusion. Much like a movie appears continuous to us, but is actually a rapid succession of still frames. Imagine time not as a flowing river, but as a series of incredibly rapid, distinct clicks, so fast that our perception blurs them into a seamless stream. This idea challenges our deepest intuitions about the continuity of existence and opens up entirely new avenues for thinking about the very structure of reality. At its most fundamental level, another perplexing aspect of quantum time lies in phenomena like quantum entanglement. Here, two particles can become linked in such a way that the state of one instantaneously affects the state of the other, regardless of the distance separating them. This spooky action at a distance, as Einstein called it, seems to defy the classical notion that information cannot travel faster than the speed of light, raising questions about causality and the very flow of time. If a measurement on one entangled particle instantly influences its partner light years away, does that imply a kind of timeless connection, or a communication that transcends the usual temporal constraints? While quantum mechanics rigorously accounts for these phenomena, their implications for our understanding of time's ultimate nature are still deeply debated and explored. It's as if, at this fundamental level, the universe occasionally winks at our carefully constructed notions of linearity, hinting at deeper, more interconnected realities. The relationship between consciousness and time also adds another layer of intriguing mystery. Our perception of time is deeply subjective. It can seem to drag when we're bored or fly by when we're engrossed. While this is largely a psychological phenomenon, some deep philosophical and even speculative scientific theories ponder whether consciousness itself plays a role in the emergence of time from a timeless quantum realm. Does our active observation, or our conscious experience, somehow collapse the probabilistic quantum states into a definitive sequence of events, thereby creating our experience of a linear past, present, and future? This is highly speculative territory, but it highlights how intertwined our most fundamental concepts of reality are with our very act of perceiving it. It suggests that perhaps the quiet tick-tock of our internal clocks is not merely observing an external reality, but might be intimately part of its unfolding, a gentle dance between observer and observed. As we gently drift through these profound concepts, it becomes clear that time, far from being a simple, unchanging backdrop, is a dynamic and multifaceted phenomenon. From the relative flows predicted by Einstein's theories to the granular, probabilistic whispers of the quantum realm, Our scientific understanding is constantly expanding, revealing new depths and challenging long-held assumptions. The quest to unify general relativity with quantum mechanics continues to be one of the greatest challenges in modern physics. And the resolution of this quest promises to illuminate the very nature of time, space, and reality in ways we can only begin to imagine. Perhaps as we continue to listen, to observe, and to ponder, we will come closer to understanding the true chronos, not just the ticking clock of our lives, but the deep, resonant rhythm of the universe itself, from its smallest, most ephemeral vibrations to its grandest, most eternal flows. And as these thoughts gently settle in your mind, perhaps they will carry you deeper into a peaceful slumber, where the very fabric of time may feel as soft and comforting as the night itself. In our lived experience, the direction of time is undeniable. Cups shatter, but never spontaneously reassemble. Eggs scramble, but don't unscramble. People age, but don't grow younger. Memories accumulate, but the future remains unknown. This unidirectional flow is so fundamental to our reality that we rarely question it. Yet, when we look at the most fundamental laws of physics, at the equations that govern the universe at its microscopic level, Newton's laws of motion, Maxwell's equations for electromagnetism, even the equations of quantum mechanics, they are, for the most part, time-symmetric. This means that if you were to record a physical process, then play the recording backward, the reversed process would still obey those fundamental laws. A billiard ball collision, if reversed, would still be a perfectly valid collision according to physics. A planet orbiting a star could, mathematically, orbit backward just as easily. This presents a profound paradox. If the microscopic laws are reversible, why is the macroscopic world we inhabit so stubbornly irreversible? Why does time's arrow fly in only one direction? The answer, it turns out, lies not in the fundamental laws of motion themselves, but in the realm of thermodynamics, specifically the second law of thermodynamics. This law is, perhaps, one of the most robust and pervasive laws in all of science, affecting everything from the decay of a fallen leaf to the ultimate fate of the universe. It states, in essence, that in any isolated system, the total amount of entropy, measure of disorder, or randomness can only increase over time or, at best, remain constant. It never decreases. Think of your room. Left undisturbed, it tends to get messier, not tidier. A drop of ink in water will disperse, increasing its disorder rather than spontaneously collecting back into a neat droplet. This natural tendency towards increasing disorder is what gives time its direction. The universe is, on a grand scale, like a perpetually winding down clock, moving from states of lower entropy, more order, to states of higher entropy, more disorder. It's a gentle, inevitable slide towards maximum randomness. Consider a simple analogy. A deck of new playing cards, perfectly ordered. This represents a low entropy state. If you shuffle them, they become disordered, a high entropy state. You can shuffle them endlessly, but they will almost certainly never spontaneously return to their perfectly ordered new deck arrangement. The probability of such an event is astronomically small. The universe, in its grand unfolding, is constantly shuffling particles and energy, moving from configurations that are statistically less likely ordered to configurations that are, statistically, far more likely disordered. The past is characterized by lower entropy, the future by higher entropy. This continuous, inevitable increase in entropy provides the cosmic pacemaker for time's arrow. It's not a fundamental law dictating which way time must flow, but a statistical inevitability about the direction in which systems tend to evolve. The universe as a whole is simply following the most probable path, and that path leads inexorably towards greater disorder. This deep connection between entropy and time's arrow has profound implications. It suggests that our experience of Time flowing forward is fundamentally tied to the universe's general expansion and cooling since the Big Bang. Moving from a state of incredibly low entropy, the highly concentrated, ordered early universe, to ever-increasing entropy as it expands, and systems become more disordered. If, hypothetically, the universe were to eventually contract in a big crunch, some physicists have speculated whether the arrow of time might reverse, with entropy beginning to decrease. However, this remains a highly speculative idea, and current cosmological evidence strongly favors a continuously expanding universe. For now, the gentle, relentless march towards increased disorder continues to define the direction of time for us. Another intriguing aspect of time's arrow comes from cosmology itself. The universe began in a state of incredibly low entropy at the Big Bang, a highly ordered, hot, dense singularity. This initial entropy state provides the necessary starting point for the second law to have meaning. If the universe had begun in a state of maximum entropy, there would be no preferred direction for time. Everything would already be as disordered as it could get, and no processes would occur that distinguish past from future. So, the very existence of time's arrow, and indeed the very possibility of complex structures like stars, planets, and life, hinges on that remarkably low entropy beginning. It's a profound thought. The seemingly simple fact that time moves forward is intimately linked to the cosmic genesis, to the universe's initial conditions. This suggests that the arrow of time we experience isn't just a local phenomenon, but a cosmic one, etched into the very fabric of the universe from its earliest moments. The concept of time's arrow also touches upon the nature of information. When something becomes disordered, information about its previous ordered state is, in a sense, lost or dispersed. If a glass shatters, the information about its original coherent form is scattered among countless fragments. The second law of thermodynamics, in this context, can be seen as a statement about the irreversible loss or spreading of information. We can remember the past because it represents a lower entropy state containing more organized information. We cannot remember the future because it is yet to unfold from a probabilistic, higher entropy set of possibilities. This connection between entropy, time, and information is a deep and active area of research, particularly in fields like black hole thermodynamics, where the concept of information loss is central to the puzzles they present. It hints that the flow of time is not just about physical changes, but about the very flow and transformation of information within the universe, a quiet stream of data being continuously rearranged. While entropy provides the most widely accepted explanation for the macroscopic arrow of time, there are other, more subtle arrows proposed by physicists. One is the radiological arrow, which states that electromagnetic waves like light always propagate outwards from their source, never inwards. We see the light from distant stars, not the light converging on them. Another is the causal arrow, which posits that causes always precede effects. You feel the heat from a fire after it's lit, not before. While these arrows often align with the thermodynamic arrow, their fundamental nature and independence are still debated. Are they merely consequences of the thermodynamic arrow? Or do they point to deeper, independent aspects of time's unidirectional flow? These are subtle, profound questions, inviting us to ponder the layers of temporal causality. Yet, despite the robust explanation provided by entropy, it's the intuitive feeling of time flowing, of a distinct now moving from past to future, remains a profound mystery, especially when we venture back into the quantum realm. As we gently discussed, fundamental quantum equations are time-symmetric. So, how does the irreversible macroscopic arrow of time emerge from a reversible quantum substrate? This is a key challenge in unifying quantum mechanics and gravity, often called the measurement problem in quantum mechanics. When a quantum system existing in multiple states simultaneously a superposition, is measured or observed, it collapses into a single, definite state. This collapse is an inherently irreversible process, seemingly creating a definite now and a progression of events. Some interpretations suggest that this act of measurement or interaction with a macroscopic environment is what introduces the arrow of time into the quantum world, pulling it into alignment with the thermodynamic arrow. It's a tantalizing thought that our very act of observation, the gentle act of perceiving, might be intimately linked to the universe's forward temporal march. The concept of a present moment or now is also particularly puzzling from a fundamental physics perspective. Relativity tells us that different observers, moving at different speeds or in different gravitational fields, will have different definitions of now. There is no universal, privileged now that all observers agree upon. This challenges our intuitive sense that a single universal present slices through spacetime, separating the past from the future. If now is relative, what then defines the continuous progression of time? This pushes us to consider whether our experience of now is perhaps an emergent property of our consciousness. A subjective slicing of the space-time continuum that is perfectly valid for our frame of reference, but not universally shared. It's like standing on a train, watching the scenery pass. Your now is the window you're looking through, but someone on another train, moving at a different speed, has a different now passing their window. Both are real, but neither is absolute in the realm of quantum gravity. Theories that attempt to unify quantum mechanics with general relativity, the problem of time's arrow becomes even more acute. Some models propose that at the Planck scale, the smallest possible scales of space and time as we know it might not exist at all. Instead, there might be a timeless substrate of quantum events, from which the macroscopic arrow of time emerges when a sufficient number of these events interact and cohere. It's akin to how temperature emerges from the chaotic motion of countless individual atoms. No single atom has a temperature, but the collection does. Similarly, perhaps no single quantum event has a time, but the vast collection of events we experience as our universe does. This would mean that time is not a fundamental building block of reality, but a macroscopic illusion, albeit a very persuasive and necessary one for our existence. It's a concept that invites us to gently question our most deeply held assumptions about reality, the irreversibility of processes in our world, the shattering glass, the aging body, the dispersal of sentience often taken for granted, but understanding its deep connection to entropy, to the universe's inherent tendency towards disorder, provides a profound insight into the very nature of time's arrow. It suggests that time is not merely a passive dimension through which events unfold, but an active participant, its direction intrinsically linked to the statistical evolution of the cosmos. As we lie here, listening, feeling the quiet passage of moments, we are participating in this grand entropic dance, a gentle, inevitable movement from order to a greater, more expansive disorder. And in this understanding, there is a quiet beauty, a serene acceptance of the universe's profound and unyielding flow. May this soft knowledge carry you deeper into a tranquil rest where the arrow of time, for a while, can be observed with a calm and peaceful awareness rather than felt with its relentless push. Imagine, if you will, two perfectly synchronized, identical clocks. In our everyday experience, we assume they would always tick at the same rate. But Einstein's theory of special relativity, published in 1905, showed this isn't true when one of those clocks is moving at very high speeds, speeds approaching the ultimate cosmic speed limit, the speed of light. Special relativity posits two fundamental ideas. First, that the laws of physics are the same for all non-accelerating observers. And second, that the speed of light in a vacuum is the same for all observers, regardless of their motion. Seemingly simple postulates lead to profound and counterintuitive consequences, with time dilation being one of the most famous. The theory predicts that for an object in motion relative to an observer, time for that moving object will appear to slow down from the observer's perspective. Let's gently illustrate this with a thought experiment, often called the light clock. Imagine a clock that works by bouncing a beam of light between two mirrors. Each bounce represents one tick of the clock. If this clock is stationary next to you, the light beam travels straight up and down between the mirrors. Now, imagine. This light clock is moving past you at a very high speed. From your perspective, as the clock moves horizontally, the light beam inside it must travel a diagonal path to hit the mirrors. Because the speed of light is constant for all observers, for the light to cover this longer diagonal distance, it must take more time. Therefore, from your stationary perspective, the moving light clock appears to tick slower. The moving clock, however, from its own perspective, sees the light beam traveling straight up and down, and for it, time is passing. Normally, this is the essence of time dilation due to velocity. Moving clocks run slow. It's not that the clock is broken. It's that time itself is literally slowing down for the moving frame of reference. This effect, though imperceptible in our daily lives due to our relatively slow speeds, becomes significant at speeds approaching the speed of light. For example, subatomic particles called muons, which are created in the Earth's upper atmosphere, have a very short lifespan. If time did not dilate, very few of them would survive long enough to reach the Earth's surface. However, because they travel at speeds close to the speed of light, their internal clocks, their decay rate, slow down relative to an observer on Earth, allowing many more muons to reach detectors on the ground than would otherwise be possible. This isn't just theory, it's an experimentally verified phenomenon, a testament to the elegant strangeness of spacetime. The universe, in its quiet wisdom, shows us that velocity is not just about distance covered, but also about the gentle stretching of moments. But velocity is not the only factor that influences the flow of time. Einstein's more comprehensive theory, general relativity, published in 1915, introduced another profound aspect of time dilation, its connection to gravity. General relativity describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. Imagine a stretched rubber sheet, and you place a bowling ball on it. The bowling ball creates a dip or a curve in the sheet, chording. To Einstein, massive objects like planets and stars do something similar, curving the very fabric of spacetime around them. And just as this curvature affects the paths of objects moving through space, it also affects the flow of time. The prediction is that time runs slower in stronger gravitational fields. To gently grasp this, imagine you have two more perfectly synchronized clocks. One is placed on the surface of a massive object, say a neutron star, which has an incredibly strong gravitational field. The other clock is far away in deep space, where gravity is negligible. General relativity predicts that the clock on the neutron star will tick much, much slower than the clock in deep space. Time literally crawls for the clock, experiencing stronger gravity. On Earth, the effect is tiny, but measurable. A clock at sea level, deeper in Earth's gravitational well, will tick infinitesimally slower than a clock at the top of a tall mountain. Or, indeed, at the altitude of orbiting satellites. This gravitational time dilation is not just a theoretical curiosity. It's a practical consideration for technologies like the Global Positioning System, GPS. GPS satellites orbit Earth at an altitude where Earth's gravity is weaker than on the surface. And they also travel at high speeds around 14,000 kilometers per hour or 8,700 miles per hour. Both relativistic effects, time dilation due to velocity special relativity, and time dilation due to gravity general relativity, are at play. Due to their speed, the clocks on GPS satellites lose about 7 microseconds per day. However, due to the weaker gravity at their altitude, their clocks gain about 45 microseconds per day. The net effect is that the clocks on GPS satellites run about 38 microseconds. Faster per day compared to clocks on Earth's surface. While 38 microseconds might seem tiny, light travels about 11 kilometers in that time. If these relativistic corrections weren't continually applied to GPS signals, navigation errors would accumulate quickly, rendering the system useless within hours. So, every time you use your phone to find your way, you are quietly experiencing the profound reality of time dilation. A gentle testament to Einstein's genius. The implications of time dilation are truly vast and wonderfully unsettling to our intuitive understanding of time. It means that there is no universal now. Two events that are simultaneous for one observer may not be simultaneous for another observer in relative motion. This concept, known as the relativity of simultaneity, dissolves the idea of a single, objective present moment that slices through the universe. Instead, each observer carries their own personal now, and their perception of what constitutes the present, past, and future is unique to their frame of reference. It's like a cosmic ballet, where each dancer moves to their own slightly different internal rhythm, yet all are part of the same grand performance. This understanding gently guides us away from the notion of time as an absolute, external metronome, and towards seeing it as an emergent property of the universe, deeply intertwined with space, motion, and gravity. Consider for a moment the concept of twin paradox. It's a classic thought experiment that beautifully illustrates time dilation due to velocity. Imagine a pair of identical twins. One twin, let's call her Alice, embarks on a long space journey. At a speed close to the speed of light, perhaps to a distant star and back. Her twin Bob remains on Earth, according to special relativity. When Alice returns to Earth, she will have aged less than Bob. From Alice's perspective, her journey was quick, and Bob's time seemed to pass normally. But from Bob's perspective, on Earth, Alice's clock and her aging process would have slowed down dramatically during her high-speed journey. When they reunite, Alice will indeed be younger than Bob. This isn't a trick or a paradox in the sense of a logical contradiction, but a genuine consequence of space-time's nature. It simply challenges our everyday intuition that time must tick universally for everyone. The paradox is resolved by recognizing that the traveling twin experiences acceleration, which shifts their frame of reference, making their journey fundamentally different from the stationary twins. It's a beautiful, if unsettling, reminder that time's gentle flow is not fixed, but dances with our movement through the cosmos. The stretching and bending of time due to gravity also has significant implications for our understanding of black holes. A black hole is a region of spacetime where gravity is so incredibly strong that nothing, not even light, can escape from it. As an object approaches the event horizon, the point of no return around a black hole, gravitational time dilation becomes extreme. From the perspective of a distant observer, time for the object falling into the black hole appears to slow down dramatically, eventually seeming to freeze at the event horizon. The object itself never appears to actually cross the event horizon. From the distant observer's viewpoint, as its light becomes infinitely redshifted and dim. However, from the perspective of the falling object, time continues to flow normally, and it swiftly passes the event horizon, inevitably heading towards the singularity at the black hole's center. This profound difference in temporal experience highlights just how deeply gravity can warp the fabric of time, twisting its gentle flow into an almost infinitely stretched-out ribbon. The study of gravitational waves, ripples in spacetime caused by massive accelerating objects like merging black holes or neutron stars, further confirms the dynamic nature of spacetime and, by extension, time itself. These waves, predicted by Einstein a century ago and directly detected for the first time in 2015, are literally distortions in the fabric of spacetime that propagate outwards at the speed of light. They stretch and compress spacetime as they pass, meaning they also subtly stretch and compress time. While these effects are incredibly tiny here on Earth, they are a direct observation of spacetime's flexibility, a living, breathing canvas that ripples and undulates with the cosmic dance of the most massive objects. It suggests that time is not just a passive dimension, but an active participant in the universe's most violent and energetic events. Responding to the cosmic drumbeat, these gentle revelations about time dilation, both from velocity and gravity, fundamentally reshape our understanding of what time truly is. It's not a universal constant, but a flexible relative dimension, deeply interwoven with space to form spacetime. This unified fabric is dynamic, bending and stretching in response to the presence of mass and energy, and shaping the very flow of moments. Our personal experience of time, while feeling absolute, is merely a slice of this grander, more fluid reality. The universe in its quiet wisdom has shown us that our intuition about time, while useful for navigating everyday life, is merely a small window into a much vaster and more intricate temporal landscape. As we bring this segment to a close, allow these ideas to gently settle in your mind. The notion that time can speed up or slow down, that a journey through the cosmos could make you effectively travel into your own future relative to those you leave behind, is a profound and beautiful thought. It dissolves the rigid boundaries of now and invites us to see time not as a fixed path, but as a fluid stream that we navigate, sometimes slowly, sometimes swiftly, through the curved and vibrant contours of spacetime. May this gentle understanding deepen your relaxation, allowing your own internal clock to find its most peaceful rhythm as you drift further into the calm embrace of sleep, carried by the very currents of time we've so softly explored. When we speak of the quantum realm, we are referring to the world of subatomic particles, electrons, photons, quarks, and the forces that govern them. This realm is described by quantum mechanics, a theory that has been astonishingly successful at predicting experimental outcomes, yet remains deeply counterintuitive. In this microscopic world, particles don't behave like tiny billiard balls with definite positions and momenta. Instead, they exist in superpositions, meaning they can be in multiple states or locations simultaneously, only choosing a definitive state when measured or observed. This inherent probabilistic nature, where certainty is replaced by a cloud of possibilities, creates profound challenges for our understanding of time. A particle can be in two places at once. When, precisely, does an event happen in the quantum world? The classical notion of a definite when becomes deeply problematic, one of the most significant puzzles regarding time in quantum mechanics is known as the problem of time in quantum gravity. This arises when physicists attempt to combine general relativity, which describes gravity and spacetime as a continuous fabric, with quantum mechanics, which describes matter and energy in discrete packets or quanta. When you try to quantize gravity, that is, apply quantum principles to spacetime itself, many formulations lead to a startling result. The variable for time simply disappears from the fundamental equations. For example, in the Wheeler-DeWitt equation, a cornerstone of canonical quantum gravity, there is no explicit time parameter. This doesn't necessarily mean time doesn't exist, but rather suggests that at the most fundamental quantum level, time might not be a continuous external backdrop as we perceive it. Instead, it might be an emergent phenomenon, something that arises from the relationships and interactions between quantum events, rather than being a pre-existing container for them. Imagine a vast, intricate tapestry. Our everyday experience of time is like tracing a single thread from left to right, seeing a clear progression. But at the quantum level, the problem of time suggests that the tapestry might be woven from timeless loops and knots, and the perception of a linear thread only emerges when you step back and observe the entire complex pattern. It implies that before and after might not be fundamental concepts at this ultimate scale, but rather statistical properties that become evident at larger macroscopic levels. It's a profound shift, transforming time from an absolute ruler of reality to a complex symphony born from countless tiny, interconnected quantum notes, each without its own inherent sunquai, each without its own inherent rhythm. Another fascinating aspect of quantum time is related to the concept of quantum entanglement. We gently touched upon this earlier, where two or more particles become intrinsically linked, sharing a common fate regardless of the distance separating them. A measurement performed on one entangled particle instantaneously influences the state of its partner, even if they are light years apart. This spooky action at a distance seems to defy the classical notion that information cannot travel faster than the speed of light, and it raises deep questions about causality and the flow of time. If an influence can be instantaneous across vast distances, what does that imply about the usual sequence of cause and effect, which relies on a progression through time? While quantum mechanics successfully describes these phenomena, the implications for the ultimate nature of time are still a subject of intense philosophical and scientific debate. It's as if, at this fundamental level, the universe occasionally winks at our carefully constructed notions of linearity, hinting at deeper, more immediate connections that transcend the conventional temporal constraints. Some interpretations of quantum mechanics, such as the many worlds interpretation, offer a different perspective on time's flow. Instead of a single reality where quantum superpositions collapse into one outcome, this interpretation suggests that every possible outcome of a quantum measurement actually occurs, leading to a splitting of the universe into multiple parallel branches. In this view, time isn't so much a linear progression as it is a continuous branching, with new universes constantly being created as every quantum possibility is realized. While this interpretation avoids the collapse problem, it creates an unimaginably vast multiverse. Its implications for our experience of a singular linear time are profound. Perhaps our flow of time is simply our journey along one specific branch of an ever-expanding, branching reality. This thought can be both wonderfully expansive and profoundly humbling, suggesting that our timeline is but one thread in an infinite quantum tapestry. The concept of quantum tunneling also subtly challenges our classical notions of time. In this phenomenon, a particle can tunnel through an energy barrier that it classically wouldn't have enough energy to overcome. It's as if the particle momentarily borrows energy to overcome the barrier, or passes through it without actually spending any time inside the barrier. Experiments have even suggested that in some cases, particles undergoing tunneling might appear to traverse the barrier faster than light, or effectively arrive at the other side before they should have, according to classical calculations. This tunneling time is a complex and debated topic, but it certainly suggests that at the quantum level, our intuitive understanding of the duration of events might not hold. It's like a whisper of a shortcut through the fabric of time, allowing momentary defiance of conventional passage. Furthermore, the very act of measurement in quantum mechanics is intimately tied to our experience of time's arrow. Before a measurement, a quantum system exists in a superposition of states. The act of measurement collapses this superposition into a single, definite outcome, an inherently irreversible process. This collapse is what brings the quantum world into our classical, macroscopic reality, where events happen definitively and time moves forward. Some theories propose that it is precisely this interaction with a macroscopic environment, which is itself governed by the thermodynamic arrow of time, that decoheres the quantum system and introduces the arrow of time into the microscopic world, effectively aligning it with the entropic flow we experience. So, the very moment of observation, of sensing and knowing, might be the gentle bridge between a timeless quantum realm and our time-bound classical reality, the ongoing quest for a theory of quantum gravity, a unified theory that reconciles. General relativity and quantum mechanics is where the deepest insights into the nature of time are expected to emerge. Various approaches, such as string theory and loop quantum gravity, offer different perspectives. String theory, which posits that fundamental particles are tiny vibrating strings, it often operates in higher dimensions, and some of its formulations hint at the possibility of time being an emergent property from these more fundamental strings. Loop quantum gravity, as we briefly mentioned, proposes that spacetime itself is quantized, made up of discrete loops of gravitational field lines. If spacetime is fundamentally granular, then time itself might be discrete, comprised of indivisible, Cronans or Planck times, approximately y-43 seconds, the smallest possible units of time. If this is true, our perception of time as a smooth, continuous flow would be an illusion, much like a film appears continuous despite being made of individual frames. This would mean that time is not a fundamental background, but something that clicks into existence at unimaginably tiny intervals. The philosophical implications of these quantum perspectives on time are immense. If time is not fundamental, but emergent, what does that mean for free will, for causality, for our sense of identity that is so deeply rooted in a linear personal history? If the past, present, and future are not absolute, but relative, or if they somehow coexist at a deeper quantum level, how does that reshape our understanding of memory, prediction, and the very flow of our conscious experience? These are not questions with easy answers, but they invite us to gently expand our minds, to consider realities far richer and stranger than our everyday perceptions allow. The universe, in its profound wisdom, offers up these quantum riddles, beckoning us to unravel them with quiet contemplation as we conclude this segment on time in the quantum realm. Allow yourself to float with these ideas. The notion that time might disappear from fundamental equations, or that it might be woven from discrete, timeless interactions, is profoundly humbling. It suggests that our intuitive sense of a universal clock ticking away is a beautifully elaborate illusion, a necessary construction of our macroscopic experience, arising from a deeper, more mysterious quantum ballet. Perhaps, as you drift towards sleep, your mind, freed from the constraints of conscious linearity, can subtly touch upon this timeless quantum fabric, experiencing a deeper serenity that transcends the ticks and talks of the everyday world. May your rest be profound, touched by the quiet enigma of quantum time. Let's begin with time travel to the future. Surprisingly, this form of time travel is not only permitted by the laws of physics, but has already been demonstrated and is a proven reality, albeit not in the dramatic, instantaneous way depicted in science fiction. Our discussion on time dilation in special and general relativity already provided the key. Remember, time runs slower for objects moving at very high speeds and in stronger gravitational fields. This means that by traveling at speeds approaching the speed of light, or by spending time near a massive object like a black hole, you would effectively travel into the future relative to someone who remained in a weaker gravitational field or at slower speeds. The twin paradox, which we gently explored, is a perfect example. The astronaut twin who travels at near light speed returns to Earth, having aged less than their terrestrial sibling, effectively having traveled into the future. Relative to them, while a significant journey into the future via velocity time dilation would require technology far beyond our current capabilities. Imagine a spaceship that could sustain speeds very close to the speed of light for extended periods. The principle is sound. Similarly, hypothetical journeys near a black hole's event horizon would offer an even more dramatic leap into the future due to extreme gravitational time dilation. For instance, if one were to orbit a hypothetical black hole just outside its event horizon for a short period, due to the extreme gravitational time dilation, thousands or even millions of years could pass on Earth while only minutes or hours passed for the orbiting individual. This form of time travel to the future is a direct consequence of the relativistic universe we inhabit. It's not a violation of physics, but a manifestation of it. It's a quiet, cosmic waiting game, where the passage of moments can be stretched by the immense forces of the universe. Now, let us turn our gaze to the far more challenging and paradox-laden prospect of time travel to the past. This is where the scientific debate truly heats up and where the most perplexing paradoxes arise. While traveling to the future is a consequence of how space-time already works, traveling to the past would seem to require a bending of space-time in ways that allow for closed time-like curves, CTC's paths through space-time that loop back on themselves, allowing an object to return to its own past. Some solutions to Einstein's equations of general relativity. Under very extreme and often unrealistic conditions, do theoretically allow for CTCs. One such theoretical possibility involves wormholes, also known as Einstein-Rosen bridges. Imagine a wormhole as a tunnel through space-time connecting to different points in space and time. While wormholes are mathematically possible in general relativity, their existence has never been observed, and if they do exist, they would likely be incredibly unstable and require exotic matter with negative energy density to keep them open and traversable. If a traversable wormhole could be created and one end was moved at relativistic speeds or placed near a black hole, time dilation would occur between its two ends. One end would age more slowly than the other. If you then entered the younger end of the wormhole and exited the older end, you could, in principle, emerge in the past relative to your starting point. It's a breathtaking, delicate possibility, a whisper of a cosmic shortcut. Another theoretical mechanism for past time travel involves rotating black holes, specifically Kerr black holes. Some mathematical solutions suggest that if one were to travel around a rapidly spinning Kerr black hole in a specific trajectory, it might be possible to enter a region of space-time where CTCs exist, allowing a return to the past. However, these theoretical paths are fraught with extreme gravitational forces, and the stability and traversability of such regions are highly debatable. It's the kind of concept that fills physicists with both awe and a healthy dose of skepticism. A powerful gravitational dance that might just loop back on itself. The greatest hurdle for past time travel isn't just the immense technological difficulty or the need for exotic matter. It's the paradoxes it generates. The most famous is the grandfather paradox. If you could travel back in time and prevent your grandfather from meeting your grandmother, you would prevent your own birth. But if you were never born, how could you have traveled back in time to prevent your grandfather from meeting your grandmother in the first place? This creates a logical contradiction. Other paradoxes include the autoconsistent paradox, where your actions in the past ensure the very future you came from, and the bootstrap paradox, where information or an object is created without an origin existing in a self-sustaining loop through time, like a book that you take back in time and then someone else copies, and that copy is then what you originally took back in time. These paradoxes suggest that either past time travel is impossible, or that if it is possible, the universe must have some inherent mechanism to prevent such contradictions. Various solutions to the paradoxes have been proposed. One popular idea is the self-healing hypothesis, or Navikov's self-consistency principle. This suggests that if time travel to the past were possible, any actions you took in the past would be constrained to be consistent with known history. You simply wouldn't be able to change anything to create a paradox. If you tried to prevent your grandfather's meeting, some unforeseen circumstance would inevitably intervene to ensure it happened. Anyway, it's as if the timeline resists alteration, gently nudging events back into their predetermined course. This principle implies that free will in the past would be an illusion, or at least significantly constrained for time travelers. Another intriguing solution comes from the many worlds interpretation of quantum mechanics, which we briefly touched upon. In this view, if you travel to the past and make a change, you don't alter your original timeline. Instead, you splinter off into a new parallel universe or branch of reality where your altered past becomes the history of that new universe. Your original timeline remains unaffected. This elegantly bypasses the paradoxes by suggesting an infinite number of parallel realities, where every possible timeline coexists. This perspective makes time travel to the past possible, but each journey creates a new history rather than rewriting an old one. It's a beautifully expansive, if somewhat overwhelming, solution to the problem of paradoxes, turning each moment of choice into a gentle branching of the cosmos. Beyond the theoretical challenges, the practicalities of building a time machine are immense. Even if traversable wormholes or CTCs could be created, they would require unimaginable amounts of energy and mentioned exotic matter with negative energies, something that current physics suggests might exist only in very limited, fleeting quantities, if at all. Furthermore, maintaining the stability of such space-time distortions would be an engineering feat far beyond anything we can currently conceive. It's a dream that pushes the boundaries of our understanding, a whispered possibility at the very edge of physical reality. The very concept of time travel forces us to confront our understanding of causality and the nature of reality. If the future can influence the past, or if multiple timelines exist, what does that mean for our sense of agency and the linear narrative of our lives? While traveling to the past remains firmly in the realm of theoretical physics and science fiction, the contemplation of its possibilities and paradoxes continues to be a rich ground for exploring the fundamental nature of time itself. It invites us to consider that the gentle flow of moments we experience might be just one facet of a far more complex and interconnected temporal reality. As we bring this segment to a close, allow the thoughts of stretched moments and potential journeys through time to gently settle in your mind. It's a scientific contemplation of time travel, while often leading to perplexing paradoxes, also deepens our appreciation for the profound elegance and mystery of space-time. Whether time travel remains a dream or eventually becomes a reality, the questions it poses about past, present, and future continue to illuminate the quantum fabric of time itself, inviting us to ponder its ultimate secrets. May these quiet contemplations guide you into a peaceful and perhaps even time-bending sleep, where dreams can effortlessly traverse any temporal boundary. Our brain, a remarkably complex organ, doesn't possess a single master clock that uniformly dictates our perception of time. Instead, it seems to rely on a distributed network of neural processes that integrate various internal and external cues to construct our subjective experience of temporal flow. This internal clock is highly flexible, influenced by a myriad of factors, including our emotions, tension, age, and the novelty of our experiences. The perception of time is, in many ways, an intricate, gentle symphony orchestrated by our own minds. Consider the common experience. Time flies when you're having fun. When we are deeply engaged in an enjoyable activity, our attention is often focused outwards, on the task or experience itself, rather than inwards, on the passage of minutes and hours. Our brains are processing novel information, creating new memories, and releasing dopamine, a neurotransmitter associated with pleasure and reward. This heightened engagement and cognitive load can make time seem to speed up because our internal missed markers, the discrete moments our brain records, to gauge duration, are so densely packed that our brain perceives a shorter elapsed period. Conversely, when we are bored or anticipating an event, our attention is often drawn inwards, dwelling on the slow passage of time itself. With fewer novel events to mark its progress, time feels stretched and prolonged. It's like staring at an empty wall versus watching a bustling street. The former offers fewer ticks for your internal clock. Age also plays a significant role in our perception of time. It's a common lament among adults that time seems to speed up as we get older. While this phenomenon is complex and likely has multiple contributing factors, one prominent theory relates to the novelty of experiences. For a child, almost every day is filled with new discoveries, learning, and first-time events. Each new experience leaves a dense trail of memories, which our brain uses to estimate duration. As we age, our lives often become more routine, with fewer truly novel experiences. With fewer new event markers being laid down, our brains perceive the same objective duration as shorter. Think of it this way: a year for a 5-year-old is a significant fraction of their entire life and filled with countless firsts. For a 50-year-old, a year is a much smaller fraction of their life and may contain fewer entirely novel experiences. The event density decreases, making time feel compressed. Emotion is another powerful modulator of our internal clock. In situations of high stress or danger, time can appear to slow down dramatically, a phenomenon often described as bullet time or a heightened state of awareness. For example, in a car accident or a sudden fall, people often report that moments seem to unfold in slow motion. This is likely an evolutionary adaptation under extreme threat. Our brains process information at an incredibly accelerated rate, allowing us to perceive more details and potentially react more effectively. This dense processing of information creates a richer, more detailed memory of the short event, which our brain then interprets as having lasted longer. Conversely, positive emotions like joy or excitement tend to make time feel like it's passing more quickly as we are absorbed in the moment. Our subjective perception of time, then, is not merely a passive observation, but an active, dynamic construction deeply intertwined with our emotional landscape. Attention is perhaps the most fundamental cognitive process influencing time perception. When our attention is directed towards time itself, for example, waiting for something, checking the clock, it appears to slow down. When our attention is directed away from time and fully immersed in a task, it seems to speed up. This attentional gate hypothesis suggests that our brain filters how much information reaches our internal timing mechanisms. The more attention we give to time, the more ticks we perceive, and the longer the duration feels. This is why mindfulness practices often emphasize focusing on the present moment without judgment. By fully immersing in the now, without anticipating the future or dwelling on the past, our experience of time can feel more expansive and less pressured. Chemical influences also subtly shift our time perception. Stimulants, like caffeine or amphetamines, can speed up our internal clock, making external time appear to pass more slowly. Depressants, like alcohol or sedatives, can slow down our internal clock, making external time appear to pass more quickly. Certain neurological conditions, such as Parkinson's disease or ADHD, can also affect time perception, suggesting specific brain regions and neurotransmitter systems are involved in our temporal processing. This underscores the biological underpinnings of our subjective experience of time, a delicate chemical dance within the brain. Even the culture we grow up in and the language we speak can subtly shape our perception of time. Some languages describe time with spatial metaphors, for example, long time, short time, while others might emphasize the sequence of events over duration. Cultural norms around punctuality or how future events are planned can also influence our collective and individual sense of temporal urgency or expansiveness. While these cultural influences don't alter the fundamental physics of time, they certainly shape our psychological and social relationship with its flow. It's a gentle reminder that even our deepest internal experiences are influenced by the broader tapestry of human interaction and shared understanding. The study of time perception is a vibrant field spanning neuroscience, psychology, and philosophy. Researchers use various experimental paradigms, from asking participants to estimate short intervals to tracking neural activity during timed tasks to unravel the intricate mechanisms behind our subjective temporal experiences. While no single unified theory of time perception exists, the evidence strongly points to a dynamic, flexible system rather than a fixed internal clock. Our brain is constantly calculating, integrating, and constructing our experience of time, moment by moment, often without our conscious awareness. It's a beautiful testament to the brain's remarkable capacity for intricate sensory and cognitive processing, transforming raw external stimuli into a rich, lived reality. The profound subjectivity of time also raises philosophical questions about the nature of reality. Time can stretch and shrink based on our internal states. Is there an objective, external now that truly exists, or is now primarily a construct of our consciousness? While physics, particularly general relativity, suggests there is no universal now from a cosmological perspective, the biological and psychological findings deepen this mystery by showing how deeply personal our lived now truly is. Our perception of time is thus a fascinating bridge between the objective laws of the universe and our unique, conscious experience of existing within it. It's a quiet reminder that the grand cosmic truths are often reflected in the most intimate corners of our own minds. As we gently conclude this segment on the subjectivity of time, allow yourself to feel the subtle dance of your own internal clock. Perhaps you notice how the quiet stillness of this moment feels different from the rush of a busy day. This awareness, this gentle observation of your own temporal perception, is a beautiful doorway into understanding the quantum fabric of time itself, not just as an external phenomenon, but as something deeply woven into the very structure of your being. May this soft understanding deepen your sense of peace, allowing your mind to drift into a restful slumber, where the gentle rhythm of your dreams might offer new, fluid experiences of time, free from its usual constraints. In our everyday experience, the present moment feels undeniably real and universally shared. We perceive a sharp distinction between the past, which is fixed and gone, and the future, which is open and yet to come. The now is the moving boundary, the point of action and awareness. This intuitive sense of a universal now forms the bedrock of our personal narratives, our collective histories, and our plans for tomorrow. We assume that when we say, "It is 7 p.m. right now," someone across the world, even in a different time zone, would agree that the event happening here at 7 p.m. is indeed happening now for them as well. After accounting for time zone differences, this seems self-evident. However, the quiet revelations of Einstein's special theory of relativity begin to gently dismantle this intuitive notion of a universal now. As we discussed, special relativity posits that the speed of light is constant for all observers, regardless of their motion. This seemingly simple fact leads to the profound consequence known as the relativity of simultaneity. Imagine two observers, one stationary on Earth and another zipping past in a spaceship at a significant fraction of the speed of light. If two events occur simultaneously for the observer on Earth, say, two distant fireworks exploding at precisely the same moment in their frame of reference, those same two events will not be simultaneous for the observer in the spaceship. 4. The spaceship observer, one firework might appear to explode before the other, or vice versa, depending on their direction of motion. This means that there is no universal objective now that all observers in the universe can agree upon. What one person perceives as now the boundary between their past and future will be different from what another person, in relative motion, perceives as now. the concept of a single universal present moment slicing through all of space-time, simply dissolves. Instead, space-time is a four-dimensional continuum where past, present, and future are not rigidly separated by a moving boundary, but rather form part of a single, interconnected block. This view is often called the block universe or eternalism, where all moments in time, from the Big Bang to the distant future, exist in some sense, just as all points in space exist. Our experience of time flowing and now moving is then an emergent phenomenon, a peculiar feature of our consciousness as we navigate this unchanging four-dimensional block. It's like gently sliding your hand along a vast, completed tapestry. Your hand's position is your now, but the entire tapestry, past and future included, already exists. The block universe model, a direct consequence of the relativity of simultaneity, is deeply unsettling to our intuitive experience. If all of time past, present, and future already exists, what does that mean for free will? Does it imply a deterministic universe where everything is already laid out? Philosophers and physicists continue to debate these profound implications. Some argue that free will can still exist within a block universe, perhaps by understanding choice as an inherent aspect of our path through this pre-existing space-time. Others find it deeply challenging to reconcile with our lived sense of agency and the open-endedness of the future. This gentle paradox invites us to ponder the deepest connections between consciousness, decision, and the fabric of reality itself. Adding another layer of complexity is the quantum realm, which we've briefly explored. While the relativity of simultaneity challenges a universal now, quantum mechanics grapples with the very meaning of when an event occurs. In the quantum world, particles exist in superpositions, meaning they don't have definite properties until they are measured. This measurement process, often called wave function collapse, seems to introduce an irreversible act into the universe, potentially creating a definite now from a realm of possibilities. However, the exact mechanism and timing of this collapse are still intensely debated. Does the universe choose a definite state at a specific now? Or is the now of collapse dependent on the observer's frame of reference, as suggested by some interpretations of quantum mechanics? The intersection of relativity and quantum mechanics in this area remains one of the most challenging and exciting frontiers of physics. Some theories, particularly those related to quantum gravity, even suggest that time might not be a fundamental property of reality at all, but rather an emergent phenomenon, as we gently touched upon. If time emerges from more fundamental, timeless interactions, then the now we experience is not a fundamental property of the universe, but a derived concept, a macroscopic illusion of sorts. This would mean that at the ultimate, granular level of reality, there is no ticking clock, no flow, just a timeless sea of interconnected events, from which our perception of a linear past, present, and future somehow crystallizes. It's like the intricate patterns that emerge from a kaleidoscope. The individual pieces are distinct, but the pattern of flow is an illusion created by their arrangement and our perspective. Yet, despite these profound theoretical challenges to a universal now, our subjective experience of the present moment is undeniable. We live in the now. We make choices in the now. Memories are of the past now-s, and anticipation is for future now-s. This points to the importance of the biological and psychological aspects of time perception, which we explored in our last segment. Our brains are incredibly adept at creating a coherent, continuous narrative of time, even if that narrative is a personal construct. The present moment for us is intricately linked to our consciousness, our attention, our memories, and our anticipation. It is the locus of our conscious experience, the gentle interface between ourselves and the unfolding universe. Some neuroscientists and philosophers propose that the present moment is not an instantaneous point, but rather a brief, subjective Temporal window, a specious present, but allows us to integrate sensory information and perceive continuous motion and events. This window can vary in length, influenced by our attention and emotional state, as we've discussed. Within this specious present, our brain constructs a coherent experience of now, even if objectively outside of our consciousness. Events are happening at different nows for different observers across the vastness of spacetime. This suggests that the now we inhabit is a beautifully intricate neurological construct, a quiet dance between our perception and the universe's objective, yet fluid reality, the ongoing search for a unified theory of quantum gravity, one that successfully merges Einstein's general relativity with quantum mechanics, is ultimately the quest to understand the deepest nature of space, time, and reality. The resolution of the problem of time in quantum gravity, and the question of whether now is fundamental or emergent, promises to be one of the most profound scientific breakthroughs of our era. Until then, we are left to gently ponder these questions, allowing them to expand our minds and deepen our appreciation for the mysteries that surround us. The universe, in its quiet wisdom, offers these riddles, inviting us to contemplate the very essence of our existence as we bring this segment to a close. Allow the gentle paradox of now to settle in your thoughts. Whether a universal present truly exists or is a personal construct, our experience of this moment, here and now, is profoundly real and the very space in which our consciousness unfolds. It is a fragile, beautiful gift. May this quiet contemplation lead you into a deeper state of relaxation where the concept of time, in its objective and subjective forms, can gently guide you into a peaceful and restorative sleep, free from the urgency of any particular now. The concept of gravitational waves emerged directly from Albert Einstein's general theory of relativity, which he published in 1915. As we gently discussed, general relativity describes gravity not as a force pulling objects together, but as the curvature of spacetime caused by mass and energy. Imagine spacetime as a vast, flexible trampoline. Placing a bowling ball on it creates a depression, and smaller marbles rolling nearby will curve towards the bowling ball, not because they are being pulled by a force, but because they are. Following the curvature of the trampoline, Einstein's theory predicted that if this curvature changed, for instance, if massive objects like black holes or neutron stars moved or accelerated violently, they would create ripples in this spacetime. Fabric, much like throwing a stone into a pond, creates ripples on its surface. These ripples are gravitational waves. However, unlike ripples on a pond that travel through water, gravitational waves are ripples of spacetime itself. They are distortions that stretch and compress space and time as they pass. If a gravitational wave passed through you, it would momentarily squeeze and stretch your body by an incredibly tiny amount, then relax, then stretch and squeeze it again, perpendicular to the first stretching. It would also subtly alter the rate at which your internal clock ticked during those fleeting moments. This effect is so minuscule that even Einstein doubted whether these waves would ever be directly detectable. Given the technological limitations of his time, he initially thought they might be too weak to ever observe. And the universe kept their secret for over a century. The direct detection of gravitational waves finally happened in September 2015, nearly exactly 100 years after Einstein first predicted them. This monumental achievement was accomplished by the Laser Interferometer Gravitational Wave Observatory LIGO collaboration. LIGO consists of two massive detectors, one in Livingston, Louisiana, and another in Hanford, Washington, separated by over 3,000 kilometers. Each detector is an L-shaped interferometer with arms 4 kilometers long. Laser beams are sent down these arms, bounced off mirrors, and recombined. If a gravitational wave passes through the detector, it subtly stretches one arm while compressing. the other causing a tiny differential change in the path length of the laser beams. This minute change is then detected as a shift in the interference pattern of the recombined light. The challenge lies in detecting a change in arm length smaller than 1/10,000th the width of a proton. An astonishing feat of engineering and precision. The very first gravitational wave detected, designated GW150914, was caused by the merger of two massive black holes. One black hole had a mass about 36 times that of our Sun, and the other about 29 solar masses. As these two cosmic titans spiraled inwards towards each other, accelerating to incredibly high speeds, they emitted a tremendous burst of gravitational waves like cosmic thunder. In the final fraction of a second, as they coalesced into a single, larger black hole, about 62 solar masses, roughly 3 solar masses of energy were converted into gravitational waves, an amount of energy equivalent to many times the total energy emitted by all the stars in the observable universe during that fleeting moment. The signal detected by LIGO was a characteristic chirp sound, representing the increasing frequency and amplitude of the waves as the black holes spiraled faster and faster, finally merging. It was a profound whisper from the depths of spacetime. The detection of gravitational waves opened up a brand new window onto the universe. Before 2015, almost all of our astronomical knowledge came from observing electromagnetic waves, light, radio waves, X-rays, gamma rays. Gravitational waves, however, are fundamentally different. They are not absorbed or scattered by matter in the same way light is. This means they can carry information directly from regions of the universe that are opaque to light, such as the immediate vicinity of black holes or the very early universe before it became transparent to light. They allow us to listen to the universe's most dramatic symphony, composed of the cosmic collisions of dense, massive objects that were previously invisible to us. It's like adding an entirely new sense to our astronomical toolkit. A gentle yet powerful new way to perceive the cosmos. Since the initial detection, LIGO, along with its European counterpart, Virgo, has detected dozens more gravitational wave events, primarily from merging black holes and, significantly, from merging neutron stars. The detection of two merging neutron stars, GW170817, in 2017 was particularly exciting because it was observed not only by gravitational wave detectors, but also by traditional electromagnetic telescopes. This multi-messenger astronomy allowed scientists to directly link the gravitational wave signal to a powerful burst of gamma rays, followed by optical light from the resulting kilonova, a type of stellar explosion, where heavy elements like gold and platinum are forged. This simultaneous observation provided invaluable insights into the origins of heavy elements in the universe, the behavior of matter at extreme densities, and the precise speed of gravitational waves, confirming they travel at the speed of light. It was a harmonious chorus. It's a profound moment when the universe sang its secrets through both ripples and light. The study of gravitational waves continues to be a rapidly expanding field. Future gravitational wave observatories, such as the planned Laser Interferometer Space Antenna, LISA, in space, will be able to detect lower frequency gravitational waves from different types of cosmic events, such as the mergers of supermassive black holes at the centers of galaxies, or potentially even echoes from the very early universe. Just moments after the Big Bang, these observations promise to shed light on the formation of galaxies, the growth of black holes, and perhaps even offer clues about the nature of dark matter and dark energy, the mysterious components that dominate our universe. Gravitational wave astronomy is still in its infancy, yet it holds immense promise for revolutionizing our understanding of the cosmos, providing an unprecedented view into the most extreme environments and the earliest moments of existence. The Detection of gravitational waves is a direct validation of spacetime as a dynamic, responsive entity rather than a static backdrop. It underscores the profound interconnectedness of space and time, demonstrating that they are not separate entities, but interwoven aspects of a single fabric, a fabric that can ripple and vibrate. When a gravitational wave passes, it doesn't just stretch space. It also subtly stretches and compresses time, causing clocks to tick at infinitesimally different rates as the wave washes over them. This further deepens our understanding of time dilation and the fluidity of temporal experience in the presence of extreme cosmic events. It's a testament to the fact that the universe is far more alive and responsive than we might intuitively imagine. A gentle giant that hums with the subtle vibrations of its most massive inhabitants. As we gently conclude this segment, allow the quiet majesty of gravitational waves to settle in your mind. These are not merely abstract concepts. They're the universe's most profound echoes. Whispers from cosmic collisions that occurred millions or even billions of years ago, finally reaching our detectors after traveling across the vastness of space-time. They remind us that the fabric of reality is not still, but a dynamic, rippling canvas, continuously stretched and molded by the dance of massive objects. And in this understanding, there is a deep sense of peace and connection to the grand cosmic symphony. May these quiet thoughts guide you into a tranquil and deeply restorative sleep, where the gentle ripples of space-time might just carry you through the most beautiful dreams. The quantum Zeno effect draws its name from an ancient philosophical paradox proposed by Zeno of Ilia, particularly the arrow paradox. Zeno argued that a flying arrow is, at any given instant, motionless in space, occupying a definite position. If it is motionless at every instant, then it cannot be moving. This paradox highlights the tension between continuous motion and discrete moments. In the quantum world, this philosophical puzzle takes on a tangible scientific form, suggesting that continuous observation can indeed halt change.con mechanics. Particles often exist in a superposition of states, meaning they are in multiple possible states simultaneously until they are measured. For example, an unstable particle might be in a superposition of decayed and undecayed states. Its wave function describes the probabilities of finding it in any of these states over time, according to the laws of quantum mechanics. This wave function evolves, and the probability of the particle decaying increases. However, the quantum Zeno effect states that if you perform repeated frequent measurements on such an unstable quantum system, you can effectively reset its decay process, forcing it back into its initial undecayed state each time you measure. It's as if the act of looking at it repeatedly prevents it from making up its mind to change. Imagine, if you will, a quantum light switch that has a 50/50th chance of flipping from off to on in 1 minute if left undisturbed. If you continuously observe it, checking its state every fraction of a second, the quantum Zeno effect suggests that you would prevent it from ever flipping on. Each observation effectively collapses its wave function back to the off state, even if it had a tiny probability of flipping in the interim. The system is repeatedly forced into its initial state, preventing it from evolving. It's as if time's gentle current, at the quantum level, can be held still by the persistent gaze of an observer. This effect is not just a theoretical oddity. It has been experimentally verified in various systems, including atoms and photons. For example, scientists have shown that by repeatedly measuring the energy levels of certain atoms, they can prevent them from decaying or transitioning to different states. The more frequent the measurements, the more effectively the system is frozen in its initial state. This phenomenon beautifully illustrates the profound and counterintuitive role of observation in quantum mechanics, where the act of looking at something can fundamentally alter its behavior and even its temporal progression. It highlights the deeply intertwined nature of consciousness, or at least interaction and measurement, and the unfolding of quantum reality. The quantum Zeno effect is sometimes described as watching the pot to keep it from boiling, or a watched pot never boils, but in a literal, quantum sense. The watching measurement doesn't just inform you about the system. It actively interacts with it, pushing it back into a particular state. This continuous interaction prevents the system from evolving naturally along its probabilistic path. It suggests that the continuous progression of events, the very flow of time as we perceive it, might be dependent on the lack of continuous observation at the quantum level. If everything were constantly observed, perhaps nothing would ever change. This deepens the mystery of how our macroscopic, constantly evolving universe emerges from a quantum realm, where such freezing is possible. The implications of the quantum Zeno effect for our understanding of time are profound. If continuous observation can prevent a quantum system from changing, does this mean that the persistence of objects in our everyday lives is somehow linked to a continuous, albeit unconscious, observation or interaction at the quantum level? If change defines the passage of time, and observation can halt change, does observation also influence the very flow of time for that system? While these are complex questions without simple answers, they hint at a deeper, more active role for measurement and interaction in the universe's temporal unfolding. It's a whisper that perhaps time's very forward march is not just an external given, but also gently coaxed by the continuous interplay of matter and energy. Beyond the freezing effect, there's also a related phenomenon called the anti-Zeno effect, or sometimes the quantum anti-Zeno effect. This is the opposite scenario, where frequent measurements can accelerate the decay or evolution of a quantum system rather than inhibiting it. This often occurs when the measurements are not perfectly strong or projective, meaning they don't force the system into a single state with 100% certainty, or when the system is coupled to an environment in a specific way. It adds another layer of complexity to the relationship between observation and temporal evolution, showing that the interaction can either slow down or speed up quantum change, depending on the precise nature of the measurement. It's like a gentle tap on a pendulum, which can either stop or quicken its swing depending on when and how you apply the force. The quantum Zeno effect and its anti-Zeno counterpart provide fascinating insights into the fundamental nature of time at the quantum scale. They underscore that time, in this realm, is not a passive external clock, but is intimately interwoven with the dynamics of quantum states and the act of measurement. It's a powerful reminder that our intuitive notions of smooth, independent time break down when we peer into the deepest layers of reality, revealing a universe far more interactive and responsive than we might have imagined. The very act of observing, of gently probing the quantum world, can subtly sculpt its temporal unfolding. The practical applications of understanding the quantum Zeno effect are also slowly emerging. In the development of quantum computers, for instance, decoherence, the loss of quantum properties due to interaction with the environment, is a major challenge. By carefully applying the principles of the Zeno effect, scientists might be able to freeze or stabilize fragile quantum states, thereby extending the coherence time of qubits and making quantum computation more robust. It offers a gentle pathway to harnessing quantum phenomena for technological advancements, allowing us to maintain the delicate balance required for these sensitive systems. It's a quiet promise for the future, a way to gently coax quantum systems into doing our bidding. As we bring this segment to a close, allow the profound ideas of the quantum Zeno effect to gently settle in your mind. The notion that observing something can prevent it from changing, effectively pausing its temporal progression. It's a beautiful and unsettling testament to the deep mystery of quantum reality and its connection to time. It reminds us that time is not just a stage upon which events unfold, but is intimately involved in the very act of their unfolding, a delicate dance between potentiality and actuality. May this quiet understanding deepen your peace, allowing your thoughts to drift into a restful sleep where the gentle persistence of your own being can find a profound, timeless calm. Our journey into the subjectivity of time already touched upon how our attention, emotions, and age can distort our internal clock. But the relationship between time and consciousness goes even deeper, touching upon fundamental questions about the nature of now, memory, and anticipation. While physics describes objective time, it is our consciousness that weaves raw sensory data into a coherent narrative of past, present, and future, giving time its lived meaning. It is the gentle symphony of our inner world that truly gives form to the passing moments. Consider the phenomenon of memory. Our ability to recall past events creates our sense of a personal history, anchoring us in a linear timeline. Yet, memory is not a perfect recording. It is a reconstructive process, often influenced by our current state, emotions, and subsequent experiences. We tend to remember novel, emotionally charged events more vividly, which, as we discussed, can contribute to time feeling compressed in adulthood, as fewer truly new memories are formed. The act of remembering, then, is a constant dialogue with the past, shaping our perception of how long ago something occurred. This fluid nature of memory subtly underscores the constructive aspect of our subjective time. Equally fascinating is our capacity for anticipation and planning for the future. Unlike the past, the future is inherently open and uncertain. Our ability to mentally project ourselves forward in time, to imagine scenarios, set goals, and plan actions is a hallmark of human consciousness. This mental time travel allows us to learn from past experiences and adapt for future challenges. It suggests that our consciousness is not merely confined to the present moment, but constantly navigates across the temporal landscape, bridging past recollection with future projection. This gentle mental dance of foresight and hindsight continually reinforces our sense of linear progression. The concept of the specious present is crucial here. While physics debates the reality of an instantaneous now, our conscious experience of the present is not a razor-thin mathematical point. Instead, it is a brief, subjective duration, temporal window within which events are perceived as simultaneous and integrated into a coherent now. This specious present allows us to perceive motion, understand spoken sentences, and experience the continuous flow of events rather than discrete, disconnected snapshots. The length of this specious present can vary depending on our attention and emotional state, further highlighting its subjective nature. It's the gentle rhythmic pulse that allows us to perceive continuity amidst the discrete moments. Some theories, particularly in philosophy of mind and cognitive science even, suggest that consciousness itself might be fundamental to the emergence of time as we experience it. If, as some quantum gravity theories propose, time is not a fundamental property of the universe at its deepest level, but rather emerges from more basic, timeless interactions, then what role might consciousness play in this emergence? Could our conscious act of observation, or the collective consciousness of living beings, somehow crystallize the probabilistic quantum reality into a definite, sequential unfolding of events, thereby giving rise to our experience of linear time? This is highly speculative and ventures into the realm of philosophical idealism, but it highlights the profound questions that arise when time, reality, and consciousness are intertwined. It whispers of a subtle dance between observer and observed, where our awareness gently coaxes the temporal fabric into being. Even simpler, biological rhythms influence our perception of time. Our circadian rhythms, governed by the body's internal biological clock, regulate sleep-wake cycles and other physiological processes, grounding us in the 24-hour cycle of Earth's rotation. Beyond this, research points to various oscillators, or rhythmic neural activities in different brain regions that contribute to our ability to estimate durations. From the sub-second precision needed for playing music to the estimation of minutes and hours. Our brain integrates signals from various internal biological clocks, creating a remarkably flexible and adaptive system for temporal awareness. These are the quiet, rhythmic pulses that underpin our sense of time. The experience of timelessness is also fascinating in relation to consciousness. In states of deep meditation, flow states where one is completely absorbed in an activity, or profound spiritual experiences, individuals often report a loss of their sense of time. The past and future recede, and there is only the eternal now. These experiences suggest that while our brain usually constructs a linear temporal narrative, it also possesses the capacity to transcend it, hinting at a deeper, more fundamental aspect of consciousness that might exist beyond the conventional flow of time. It's a gentle invitation to explore the quieter, more expansive dimensions of our own awareness. The study of how the brain processes and constructs time is an active and complex field, drawing on insights from neuroscience, psychology, and even quantum physics. Brain imaging studies are revealing the neural networks involved in time estimation, memory recall, and future planning. Researchers are investigating how disorders of consciousness or brain damage can profoundly alter a person's experience of time, sometimes leading to a fragmented sense of self or a feeling of being perpetually stuck in a single moment. These studies underscore the intimate connection between the integrity of our neural architecture and our ability to perceive and navigate time effectively. It reveals the fragile elegance of our internal chronometer, the very mystery of consciousness itself. Its emergence from complex neural activity is deeply intertwined with the mystery of time. If consciousness is not merely a passive recipient of external reality, but actively participates in its construction, then our perception of time, and perhaps even its very unfolding, becomes a profound co-creation between the universe and our minds. This perspective invites us to view our own conscious moments not as isolated points, but as intricately woven threads in the quantum fabric of time itself, each thread contributing to the vast and ever-unfolding tapestry of reality. As we gently conclude this segment on time and consciousness, allow the serene thought of your inner clock to settle. Recognizing that your perception of time is a uniquely constructed, dynamic experience, shaped by your thoughts, emotions, and biology, can be deeply liberating. It invites a quiet appreciation for the intricate workings of your own mind and its profound connection to the universal flow. May this soft understanding deepen your peace, allowing you to drift into a restful slumber, where the gentle rhythms of your consciousness might experience time in its most serene and boundless forms. Our understanding of the end of time is intimately tied to the ultimate fate of the universe, a field of study known as cosmology. The universe began with the Big Bang, a state of incredibly low entropy and immense energy, approximately 13.8 billion years ago. Since then, it has been expanding, cooling, and becoming increasingly disordered, a continuous manifestation of the second law of thermodynamics, which dictates the arrow of time. The question then becomes, what happens when this expansion continues indefinitely, or if it reverses, or if some other exotic phenomena come to pass? One of the leading theories for the universe's ultimate fate, supported by current observational evidence, particularly the accelerating expansion of the universe due to dark energy, is the Big Freeze or heat death. This scenario posits that the universe will continue to expand indefinitely, causing its matter and energy to become more and more dispersed, leading to a state of maximum entropy. Over truly immense timescales, stars will burn out. Black holes will eventually evaporate through Hawking radiation, and the universe will become a cold, dark, incredibly dilute soup of elementary particles and photons, all at a uniform, near absolute zero temperature. In such a state, no further thermodynamic processes can occur. No information can be exchanged, and no events can distinguish one moment from the next. Time, in a meaningful thermodynamic sense, would effectively cease to flow. There would be no change, no increase in disorder, no arrow. It would be a gentle, silent fade into eternal stillness. Another, less favored, accused but historically significant scenario is the Big Crunch. This theory suggests that if the universe's total mass and energy density were high enough, gravity would eventually halt the expansion and cause the universe to contract. The galaxies would rush back together, eventually culminating in a reverse Big Bang, perhaps even collapsing into a singularity. In such a contracting universe, some theoretical physicists have speculated whether the arrow of time might reverse, with entropy beginning to decrease. However, current cosmological data strongly suggests that the universe's expansion is accelerating, making a Big Crunch highly unlikely. Yet, the contemplation of such a reversal invites us to gently ponder the symmetrical possibilities of time. Then, there's the more dramatic and perhaps terrifying scenario of the Big Rip. If the repulsive force of dark energy continues to strengthen over time, it could eventually become so powerful that it would overcome all other forces, including gravity, electromagnetism, and even the strong nuclear force. In this scenario, galaxies would be torn apart. Then stars, then planets, then atoms, and finally even subatomic particles themselves would be ripped into oblivion. In such a violent, absolute end, time would cease, not because of a gentle fade into disorder, but because the very fabric of spacetime and the matter within it would be shredded into non-existence. It's a cosmic unraveling, a forceful cessation of all temporal flow. These are the grand cosmic fates dictated by our understanding of classical general relativity and thermodynamics. But what of quantum possibilities? When we bring in the enigmatic principles of quantum mechanics, the end of time might take on even stranger forms in some theoretical frameworks of quantum gravity, particularly those where time is seen as an emergent phenomenon rather than a fundamental one. The very concept of time might simply dissolve at the ultimate scale. If time emerges from the complex interactions of quantum events, then perhaps in the extreme conditions of a universal end, whether it's the Big Freeze's ultimate dilution or a more exotic quantum transition, the conditions for time to emerge might simply cease to exist. This wouldn't be an end of time in the sense of a clock stopping, but rather a dissolution of the very structure that gives rise to our perception of temporal flow. It would be a return to a timeless, fundamental quantum state, a serene, eternal now beyond our comprehension. Furthermore, quantum fluctuations, those tiny, spontaneous appearances and disappearances of particles and energy in empty space, are always at play. Even in the cold, dark emptiness of a Big Freeze, these fluctuations would persist. Could these tiny quantum stirrings, over unimaginably vast stretches of non-time, eventually lead to a new Big Bang, a cosmic rebirth from the ashes of a previous universe? This cyclical model, sometimes referred to as the Big Bounce, suggests that the universe might undergo endless cycles of expansion and contraction, each culminating in a Big Crunch that immediately rebounds into a new Big Bang. In this view, time would not truly end, but would be part of an infinite, oscillating rhythm, an eternal cosmic breath. The idea of the end of time also connects to the profound mystery of black holes. As we discussed, time slows down dramatically near a black hole's event horizon. If the universe were to eventually contain only black holes, and these black holes slowly evaporated via Hawking radiation, a quantum mechanical process where black holes emit particles and energy over immense timescales, then time for any observer still existing near these dwindling remnants would experience extreme time dilation. Eventually, as the last black hole evaporates, the universe would be left with only photons and other elementary particles. What happens to time then, in the absence of any significant gravitational wells or thermodynamic gradients? It becomes an incredibly subtle and profound question, a gentle whisper at the edge of existence, the ultimate fate of time. And indeed, the universe remains one of the greatest unsolved mysteries in physics. It pushes the boundaries of our current theories and invites us to contemplate scales of existence that are almost beyond human comprehension. Yet in this contemplation, there is a quiet beauty, a profound sense of perspective. We are living in a moment where stars still shine, where life flourishes, and where time flows with a discernible arrow. Whatever the ultimate end, our present existence within the quantum fabric of time is a precious and vibrant unfolding. As we gently conclude this segment, allow these vast cosmic possibilities to settle softly in your mind. The thought of time's ultimate end, whether a gentle fade, a violent rip, or a return to timeless quantum states, can be both humbling and strangely comforting. It reminds us of the fleeting beauty of our own temporal existence and the immense, enduring mysteries of the cosmos. May this quiet contemplation lead you into a deeper state of relaxation, where the grand sweep of cosmic time can gently carry you into a profound and dream-filled sleep. A serene part of the universe's unfolding story. Even after all this quiet contemplation, all these scientific revelations, time continues to captivate us. We still look up at the night sky, mesmerized by the ancient light of distant stars, light that has journeyed across unimaginable stretches of space-time to reach our eyes. We still marvel at the quiet hush of a bird gliding on a breeze, its flight a testament to millions of years of temporal evolution. We still crane our necks to follow the silver arc of a distant airplane, a symbol of humanity's own brief but ambitious journey through the temporal currents. Time, in its multifaceted forms, reminds us how vast the universe is, and how much we have yet to gently understand. From the first delicate flutter of ancient insect wings, millions of years ago, to the thunderous roar of rocket engines piercing the stratosphere, hurtling towards orbits where time behaves differently. Time has always been more than a mere measure of duration. It is a symbol, a dream, a quiet yearning etched into the very core of our imaginations. Children instinctively stretch their arms out like wings, dreaming of soaring through the temporal flow. Artists paint canvases filled with cosmic vistas and figures suspended in moments that stretch into eternity. Pilots, who spend their lives navigating the physical dimensions of the sky, often speak of being up there as something sacred, a solitude, a serenity, a sense of perspective on time that cannot be gained from the ground below. The quantum fabric of time, in all its complexity, doesn't belong to any one creature or country. It has been shared across immense stretches of chronological existence by tiny, buzzing dragonflies and soaring swifts, by colossal feathered dinosaurs and vast flocks of migrating geese, by daring gliders, intrepid astronauts, and perhaps, one day, by quiet travelers heading to orbit for a weekend escape from Earth's temporal pull. Time is open, infinite in its possibilities, and deeply humbling in its profound mystery. And in its very essence, it invites us to imagine what else might be possible. What other temporal realities might await our gentle discovery. We are driven to understand time because we are curious about what lies within its depths, how things truly work, how far our understanding can stretch, and where its flow might ultimately lead us. But we also seek to comprehend time because it brings us closer to something we can't quite name. Perhaps it is a sense of freedom from its relentless march, or a new perspective on our place within the grand cosmic narrative. Or perhaps it is the strange, still thrill of simply being suspended between the past that defines us and the future that awaits, nestled between the Earth and the distant stars, aware of the quiet ticking of the universe's ultimate clock. understanding. Time, in its relativistic, entropic, and quantum forms, is not merely a technological feat. It is, at its heart, a profoundly human one. It took centuries of quiet contemplation, of meticulous trial and error, of scientific inquiry scribbled into notebooks and tested in wind tunnels. It required leaps of faith and careful, precise calculations. It took patient observers watching, birds sketching their ideas, building odd machines, and quite literally running into the wind with nothing but hope and canvas, driven by a deep conviction that maybe, just maybe, we too could rise above the conventional temporal flow and grasp its deeper nature. And rise we did, not just into the sky, but into a more profound comprehension of the temporal dimension itself. We have floated gently in balloons, soared gracefully in jets, hovered with precision in helicopters, and tumbled weightless in orbit, experiencing time in its most extreme manifestations. We've carried cameras to capture its fleeting moments, telescopes to peer into its ancient past, supplies to sustain its unfolding present, and dreams to shape its future into the boundless expanse of the sky. We've gently dropped seeds to nurture future growth, delivered aid to those in need, mapped glaciers revealing the slow hand of geological time, and looked down on the clouds that once seemed an impenetrable barrier, only to realize they were just part of the vast, complex, and beautiful temporal landscape. Every flight, every discovery, every quiet moment of understanding time, in its own gentle way, tells a story of persistent problem-solving, of unwavering dedication, of reaching out and not letting the perceived limitations of gravity or time itself be the final word. Even now, as our understanding of time becomes more familiar, more ingrained in our scientific narrative, it has not lost its magic, its ability to evoke profound serenity and wonder. A quiet early morning flight, witnessing the sunrise as time flows relentlessly forward. The first launch of a new rocket, its roar a temporal marker of human ambition. A hummingbird hovering at your window, a tiny marvel of temporal precision. The sheer improbability of something as complex as time in its quantum fabric, flowing gently yet precisely, allowing for the astonishing dance of existence. These are moments that don't need elaborate explanation. They simply invite us to feel wonder, to be present in the quiet flow of our own now, and to embrace the serene beauty of the temporal reality we inhabit. And so, here at the end of our gentle journey through the quantum fabric of time itself, from its relativistic stretches to its quantum whispers, we return to where we began, to the simple, profound act of quiet contemplation. Where are you listening from tonight, dear friend? And what time is it, precisely, in your part of the world, as these words gently settle around you? Are you under a midnight sky, perhaps filled with the ancient light of distant stars? Their journey a testament to time's vastness. Or is it early morning, with the soft, gentle sound of birds just beginning to stir, marking the quiet, rhythmic flow of a new day? Maybe you are peacefully winding down from a busy day, letting the stresses gently dissipate. Or perhaps you are lying in bed, letting your thoughts drift effortlessly upward like a single leaf caught in a gentle breeze, carried by the subtle currents of time. Wherever you are, whatever the hour, thank you deeply for spending this quiet time here with me, allowing your mind to gently explore the universe's most profound mysteries. If you found comfort and gentle enlightenment in this tranquil journey through the quantum fabric of time, I would be so incredibly grateful if you would leave a quiet like, or perhaps even subscribe to The Calm Scientist for more gentle explorations like this one. I always love hearing from you, so please softly let me know in the comments where you're listening from and what time it is. As you begin to gently close your eyes, preparing for a peaceful transition into dreams, and if you're still awake, gently drifting, I sincerely hope that the wonder of time itself fits history. Its science, its profound beauty, its quantum mysteries has left a soft, comforting imprint on your imagination. Whether you dream of gliding through curved spacetime, soaring over eons, or simply watching the horizon tilt as moments stretch and bend, may your sleep tonight carry you somewhere light and boundless, touched by the timeless serenity of the universe. As always, please remember, this video and its content are for entertainment and relaxation purposes only, and are not intended to provide any form of medical advice. Thank you for listening, and until our next quiet exploration, keep observing, keep wondering, and keep looking inward and upward.